क्या ठीक है? Is light is okay? Okay folks, so we are back in the econometrics class. Our rest of lectures will be on Friday and Saturday as per the new schedule which has been put up. Right? The class is on Friday and the class on Saturday. Now let me sort of get back to what we're doing. Right, so what are the things that we have looked at so far? We have looked at dealing with heteroscedasticity, right? We have looked at dealing with autocorrelation, okay? Right? Then there is the issue of multicollinearity. That's the third issue that we need to take a look at, right? Okay? So that you have right? Okay? And you know for example, so let's start with a simple model. Maybe there is no alpha. Let's start with this. We know that variance beta 1 hat right? We know that you can derive this expression. We did that, no? We did that when we did x1 and x2, right? So what it means is that if x1 and x2 are highly correlated, then the variance of beta 1 hat will be high. We know that when x1 and x2 are highly correlated, variance of beta 1 hat will be high. When there is no correlation between x1 and x2, you will get the variance of beta 1 hat, which would have been the same as that in the OLS regression. Right? So tell me one thing. If you have a variable x1, so you first have a regression. You regress y on x1. And you got some beta 1. And the beta 1 was statistically significant in the sense you rejected the null hypothesis that beta 1 is equal to 0 because the t value was large. Okay? So your first regression is y is equal to alpha plus beta x1 plus some error term t. And you found that the t value was large, so you rejected the null that say beta 1 is equal to 0. Then you put in another variable x2 in the regression model, and you found that beta 1 the t value for beta 1 became small. The t value for beta 1 hat became small, so beta 1 hat became statistically insignificant. Right, so your first model says that x1 affects y, your second model is now saying that once you include x2 in the regression model, x1 is no longer affecting y. Because the coefficient of x1 has now become statistically, the t value is not very large, so you cannot reject the null that beta 1 is equal to 0. How would you analyze this situation? What is happening? So somebody who's trained in econometrics, how would you understand this situation? Yeah? Let's see something up front, no?
So there's a limited variable x2, like there was a limited variable x2, but we bring it into the regression model, but it is correlated to only x1 and not y, not ei.
Had it not been correlated with y, you should not have put it in the regression equation, right? And if it's not correlated to y, it could not have an omitted variable because it could not have in the regression in the first place. So seeing something in there, well, how does that tell you? What does that tell you? So why is the t-value on beta 1 small now? Why would the t-value on beta 1 become small when you included x2? Why would the t-value on beta hat 1 be small now when you included x2 in the regression model? When does the t-value become small? When the variance is large. So obviously, once you put in x2, the variance of beta has increased, right? Sure? The variance of beta. Now, can you figure that out and say something from there? You got it? Correlation between? Yeah, so basically, because the variable you included x2 is correlated with x1, the variable which you have included in the regression model, right? Okay, you will have the variance of beta hat 1 will actually go up. The variance of beta hat 1 will actually go up. Can you see that? So if you include a variable in the regression model which is correlated with variables which have which have already been included in the regression model, what will happen is what might happen is the coefficients of the previously included variables might become statistically insignificant. The t-values might become large. The standard errors might actually go up, right? But then should you include such a variable or should you not include such a variable? So what happens if t-values become small? What happens? What is the implication of the t-value becoming smaller? Your ability to reject a null goes down. You are less likely to reject a null even when the null is not true. So the power of the test declines. The power of the test is the probability with which you reject a false null. The probability with which you reject a false null will go down when you include x2, right? When you include x2 in the regression model, and if x2 is correlated with x1, the power of the test will, therefore, the power of the t-test on beta hat 1 will go down. Is this clear? Power of t-test on beta hat 1 will go down. Right. So should you exclude x2 or should you include x2 in the regression model or should you not include x2 in the regression model? Should you include x2 in the regression model or should you not include x2 in the regression model? You should include. So what she's saying is yes, so unless you include x2 in the regression model, you will actually have a correlation with the error term and the explanatory variable with x1. So in the first model probably because you did not have x2 and x2 was a relevant variable, its effect was captured in the error term, and because x2 was correlated with x1, you might have a situation where you had an omitted variable bias, right? So therefore including x2 will help. Including x2 will help, right? So as an econometrician, how would you argue this situation? So somebody will say that, okay, you included x2, but because you included x2, the standard errors on beta hat 1 has gone up. So precision on beta hat 1 has gone down. The precision for beta hat 1 has gone down. So how will you argue this argument?
Can we do an ideal estimation?
Yeah, so tell me what are the various ways of answering this question. What is the best way to estimate a model? Ronak says one of the ways is to have an instrumental variable estimator for x1. right? Because there is an omitted variable bias there. But that will also include increase the variance of x1, beta hat 1, right? By 1 upon r square, by 1 upon r square, right? That factor will be there, right? So how does one evaluate the whole thing? What will be your response to a situation where the criticism is that because you've included x2 in the regression model, the coefficient of beta on x1 is now seeming to be statistically insignificant, so the t-test has lost power, right? So one argument could be, so you could argue that if there is no x2, there is an omitted variable bias, but if there is x2, then the t-test on the on x1 has a lower power, right? So between these two, how will you judge? How will you judge? Use your mind. You don't need to look at your notes.
Maybe should look at consistency rather than unbiasedness.
Okay. But it's neither consistent nor unbiased. So both ways it doesn't work. So what would be your argument? Throw out ideas. See, nobody is going to kill you if you give a wrong answer. I am not carrying a gun or anything. So
Use a different test of hypothesis.
what different is? Shoot. काहीतरी बोला ना. Say something. At least sing a song. Say something. Yeah. What would be your response? काय म्हणशील तू? What would be your response to this situation? x2 जर घातलं the variance of beta hat 1 increases. x2 नाही घातलं तर the estimator is not unbiased. There is a omitted variable bias. So काय करायचं? What is the more important thing to do? Yeah? Should you include x2 or should you not include x2?
Include x2.
He says include x2. Who says not include x2? And you are interested in beta hat 2. You are interested in beta hat 1. You are interested in whether beta hat 1 matters, right? Include करायचं की नाही करायचं? हा म्हणतो करायचं. का करायचं? Why? He says we'll have more data. Is that right or is that wrong? If you increase the list of explanatory variables, you have more data or less data? You have less data because you have fewer degrees of freedom. Because with the same set of observations, you are estimating more and more parameters. So you actually have less data. करायचं की नाही करायचं? Let's have a debate.
So if you don't include, then our x1i and ei will be correlated, which we call the problem. But that is still manageable. Like that is
Yes,
not.
that's an instrumental variable which will then be unbiased and
How is the
consistent.
test?
And
If I take an instrument for x2 in this case, which is correlated with x2 but not with x1, that can help solve it.
Okay. Any more ideas on this? These steps are getting a little bit closer to the truth. So can you either help them or obstruct them?
Which is not correlated with x2.
Uncorrelated.
but x1 is correlated with x2.
You need IV.
So suppose you put an IV. Suppose you put an instrumental variable for x1. What will be the relationship between the variance of beta hat 1 IV and, when you put, so you have an instrumental variable here, right, for beta hat 1 IV. But will you then include x2 in the regression?
Yeah.
But if you have x2 in the regression, you don't need an IV.
So if you exclude x1, then
Only if you exclude x2, you need an IV. Yeah. Only if you exclude x2, you have an omitted variable problem. If you don't exclude x2,
So if you remove x2 and bring in another IV estimator, it will do the same work that x2 is doing right now by increasing the variance of beta hat IV, which is more than beta hat variance.
so what would be your response to the answer, to the question? See, you see the dilemma, right? If I include x2, I increase the variance of beta hat 1. If I exclude x2, then the variance of beta hat 1 is not high, but the variance, the estimators could be unbiased and inconsistent, could be biased and inconsistent. So what would your solution be? What would your answer to this question be? I'm still waiting for the correct answer.
So I did not understand why if we do an IV on x1, we'll have to remove x2.
Because if you put x2, then there was no need for an IV on x1, because the problem was you needed an IV on x1 because you had omitted x2 from the relation.
No, I did IV on x1 because x1 and x2 were correlated, and I'm saying that
No, but so if you have an IV on x1, you don't put an IV on x1 because x1 and x2 are correlated. You put an IV on x1 because x1 and the error term are correlated.
yeah, but irrespective, if I put an IV on x1 with x2 in error term, so as long as my instrument for x1 is not correlated to both of them, it should be fine, right?
No, come again.
As long as my instrument for x1 is not correlated to both x2 and EI, it should be fine, right? Then I can just run the regression.
So what do you think will be the variance of the IV estimator? If I okay, let's get into this more complicated question now. Do you realize what he's saying? He's saying that we have an IV for x2 and this IV is not correlated with right? Okay. So what's the variance of the IV? The variance of the IV right? Which is equal to this still high, no? This still matters. This still matters. No? Correlation between x1 and x2 will still matter. So what will be the response? My response would be that please don't worry that the standard error of beta hat 1 has increased, because as beta hat 1 was not an unbiased estimator for beta, the formula that we have used to produce the standard error of beta hat 1 on the computer is wrong. When do you get this as a formula? You get this formula. You get this formula only if you have, right? So only if you do expectation beta minus beta square, you get sigma square upon summation xi minus x bar square, right? So using sigma square upon summation xi minus x bar square as the variance of beta hat assumes that the OLS estimator is unbiased and consistent. If the OLS estimators are not unbiased and consistent, then the omitted variable bias anyway, this would really not have been the formula for the variance of beta hat 1 in the first place. So the formula which the computer is showing for the variance of beta hat 1 OLS was anyway wrong when there was an omitted variable bias. If you have omitted variable bias, then that formula becomes a different formula. Right? What would that formula become? That formula would be this is, no? Yeah? So, variance of beta at OLS would have been variance of beta, which is a constant, plus plus 2 covariance beta this is 0, right? This is 0. So variance of beta at OLS would have been variance of summation xi ei upon summation xi square, and we don't know what that quantity is because x and e are not independent of each other. Right? Should have been some unknown formula. It would not have been variance of beta at minus beta is summation expectation of summation xi minus xi square and so on and so forth. Right? It's only because we assume expectation xi ei upon summation xi square to be 0 that we get the formula variance of beta is equal to beta or sigma square upon summation xi minus xi square. So if beta hat is not an unbiased estimate in the first place, then the formula which the computer was showing for the variance of beta hat was anyway wrong. Right? So it doesn't really matter anyway. Sure? Okay? Fine? So therefore, what you do is, basically this formula comes about. So this formula is the variance of beta hat OLS only if the estimator is unbiased. If the estimator is unbiased, then that formula is not correct. Then you actually get some other formula, right? So this argument that if you include x1, if you include x2 in the regression model, okay, variance of beta hat 1 increase and therefore you should not include x1, x2 in the regression model doesn't work. Right? Doesn't work because if x1 and x2 are correlated and x2 is an important variable in the regression model, and so what really matters is whether x2 should be included or not included in the first place. Whether x2 should be included or not included, that's what matters in the first place, and that is given by, so you have to take the test of hypothesis beta hat 2 minus 0 upon sigma hat beta hat 2, right? And that will be a t-test. So you take a t-test on beta hat 2 as well, and you find the t-test in beta hat 2 is statistically significant, the t-value is quite large, then it is important that you include beta hat 2 in the regression model. But the whole problem is that, that might not be easy to take because just like x1, x2, because x1 and x2 are correlated, the t-values of beta hat 1 and beta hat 2 might look to be too small. Right, so there is some correlation between x1 and x2, then you would know that the variance of beta hat 1 and beta hat 2 are likely to be overstated. But then by what factor you know? You know what is the factor by which the variance is overstated? 1 upon 1 minus r square. So take x1, take x2, look at the correlation between x1 and x2, right? If that correlation is so figure out 1 upon 1 minus r square. We know that's called the variance inflation factor because that increases the variance of beta hat 1. So if you take the variance of beta hat 1 and variance of beta hat 2 and divide both by the variance of inflation factor, you will know what the original variances are, right? And then you will be able to take tests of hypothesis on them and see whether those values are significant or not significant sensitive. Sure? One upon 1 minus r square. No, when x1 and x2 are correlated. When x1 and x2 are correlated, then because that is the variance inflation factor. Right? That is the variance inflation factor. The variances in the two cases will be overestimated.
So what are we using the notation as?
Sigma hat, beta hat 2.
Beta hat 2 minus
0.
0.
Beta hat 2. So
what do you mean by
What does the variance equation factor say? The variance equation factor says that the variances of beta hat 1 and beta hat 2 will be inflated by a factor 1 upon 1 minus r square because x1 and x2 are correlated. So we know that there is a downward bias in the t statistics. Right? There is a downward bias in the t statistics. Right? So therefore, you must always account for the fact that there will be a downward bias in the t statistics because x1, x2 are correlated when you are deciding whether those values are statistically significant or not significant. Right? So if you had a p-value of say 0.10, 0.11%, you would say I am going to use a 10% significance level, so this seems to be insignificant. But if x1, x2 are correlated, you need to figure out the fact that that p-value could be large, not because the genuine p-value is 11%, but because there is correlation between x1 and x2, the p-value is small, so the p-value is looking to be large. Right? So you must therefore, then you must take a call, right? Okay, so therefore it's very important that you understand. On the other hand, if you find that the correlation between x1 and x2 is small, but the p-values are really large, then you would say that the effect is not really because of the correlation. Yeah, that should be because they genuinely their variances are large, right? Okay, so that's very therefore it's very important for you to be sensitive to the correlation between x1 and x2, and also understand that when you include explanatory variables in the regression model, the t-values of one regression of variable which are already included might change. Right? In fact, if another test is, if indeed x2 were an important variable and it was genuinely an omitted variable, so by including x2, not only should the t-values of x1 change, but also the coefficient of x1 would change a lot. Because when you dropped x2, you had an omitted variable bias, so expectation of beta hat was not beta. As you saw in the did we do a computer exercise in one of the classes? We saw the distribution of beta at 1 was very far off from beta. So, but if you have included x2 now, that whole distribution will shift to the correct beta. So there will be a huge change in the parameter estimate of beta at 1. So not only will the parameter estimates of beta at 1 change, but also the p-values will change. Right? So many times, as you work with real life data, you realize that if you include x2 in the regression model, not only do the t-values of the pre-existing variables change, but their coefficients also change a lot. Right? Their coefficients also change a lot. And please remember that is because previously that means that x1 and x2 are correlated and x2 is an important variable. So previously if you had excluded it, there was an omitted variable bias. And therefore, now, of course, you must include x2 in the regression model, but you must be careful that the t-values that you are going to get have a downward bias because of the correlation between x1 and x2. Right?